But
Okay, so
on your
I'll
mark.
start as a moderator.
Hmm.
So, good afternoon to everyone, and I heartily welcome Dr. Max Telenova for this international congress organized by the Department of Computer Science, the Anand Sagar College of Engineering. It's my privilege to introduce Dr. Max Telenov, a distinguished researcher in the field of artificial intelligence and neuromorphic systems. Dr. Telenov currently serves as a senior research associate at the Institute of Artificial Intelligence, Novi Sad, Serbia, and holds academic appointments as associate professor at Kazan Federal University, Russia, and the University of Messina, Italy. With a PhD in mathematics and a strong foundation in mathematical modeling of complex systems, his research spans neuromorphic computing, memoristive systems, neurointerfaces, bio-inspired cognitive architectures, robotics, and brain-machine integration. He has authored several high impact publications in leading journals and collaborated with renowned international institutions, including INSERM France, Mayo Clinic USA, and CNR IMEM Italy. His work bridges rigorous theory with real world applications, offering valuable insights into the future of human centric and intelligent technologies. So his interest completely aligned with the interest of today's international congress, wherein we have coined Industry 5.0 human centric and sustainable development. Dear participants, please join with me in welcoming Dr. Telenova as I invite him to take this platform and share his expertise with us. Over to you, sir. Thank you.
Yeah, hello everyone. Thank you very much for having me. Okay, it's a pleasure to have all of you today here. Okay, so we are going to talk today about the future of artificial intelligence and neural networks as I see that. And so first of all, we have to identify what are the problems. And here we go. So it's well known and well discussed at the moment that there are these kind of problems that current feed-forward architectures they uh, they consume a lot of information. They have to consume a lot of information to be trained, and there's processing of this information like terabytes uh, actually comes with cost, and the cost is terawatts of energy. And we know that, well, when it's terawatts, it's even a lot of money. So the systems are still fragile. You have to put a lot of effort in mainly what is called data science. You have to process data sets, you have to prepare the data, and you have to invest a lot of time, a lot of manpower in preparing the data to make the system more or less stable. Otherwise, you get unpredictable results and it's still fragile. So still having a lot of efforts, still having this a lot of investments in that, you still have the fragile system. But okay, what are the other ways to do things? So from what my let's say scientific group will how we look at that. So there are neural networks. Neural networks were inspired by the brain, by the well, natural networks. And so we are getting the inspiration, we're trying to understand how we get this stable, this processing power that we have in the brain, and how we can translate that into the current state-of-the-art electronics. So the comparison. Recently, we published the article regarding the energy consumption. We compared in the way we could uh, the energy consumption of modern artificial neural networks. And here you can see those dots that this one are CPUs and this one are CPU. The scale is logarithmic. Just pay attention to that. And here is the energy consumption of brain and what we call memristors or artificial synapses. So synapse, if you don't know, it's a contact between two neurons. So there is, let's say, electronical element. We are going to talk about that in details a little bit later. So there are those elements that you can use. These are synapses, and you can create the network from that. So energy consumption of those elements are like here close to the brain, and even later we have updated our data. They could even outperform the human parameters, let's say, or mammalian parameters like rats and cats and so on. So the gap is really big one. The gap is like several orders of magnitude. It's like from 6 to 8 orders of magnitude. And but this is the potential. How can we improve the technology? How this could be better? And okay, and what are the reasons of that gap? So here is this diagram. There are several reasons that we could indicate. There are, for example, that I mentioned, there is feed-forward architecture that is widely used. This is well-known approach in transformers and everywhere. So you have this, oops, just feed-forward architecture here. But what in the brain, in the natural neural networks, in natural neural networks, we have a lot of feedback loops. Feedback loops, it it's a way, let's say that you could self-train. So you have this output, input and output, uh, let's say collaboration in the feedback loop. And you could, because of the feedback loop, you could play with that and create self-organizing system. Self-organizing system has the potential to save a lot of energy. So feedback loops lead us and provide us an option to create self-learning architecture, self-learning neural networks. Then there are the other things connected to membristors. So if in the digital system, you have to update the weights because of backpropagation, you have to update the weights of every connection or every synapse, or every weight actually. And there are millions and billions parameters now. But in the biological systems, or if you use membership devices, you can update only one weight if you need it. So you save the energy, not updating the weights all the time on every step of your, let's say, calculation or learning or training. You can update the weight only when you need that. And so this is the main causes of how can we save the energy, and that's why our nervous system, our brain consumed only 20 watts. When if you compare that to okay, I don't have this picture, sorry, but if you compare that to current, for example, ChatGPT version 3, they consume terabytes of energy. That is comparable to the volume of energy that being consumed by Sweden, small country, not just one brain. And one brain is just a small light bulb. Okay, how can we do that? So as we see that, the problem is the hardware. So digital hardware consumes a lot of energy by itself. So but in biology, the hardware that we have in our heads consume much less energy. So can we create some kind of electronics or some kind of approach to that to consume less energy and still having a lot of, say, cognitive functions, not just learning, but cognitive functions, still keeping this number. So in 2005, Viktor Yeroshin, with whom we collaborated a lot, he's from Parma. He invented organic membrane device, which is presented here. And so you can see that, well, the thing, the idea of membrane device is it's resistor, so it's a resistor plus memory. It has memory. And so the idea is that it remembers the current that goes through that device. It's similar to what we have in synapses in our head. So this is the basic learning mechanism that we have in immersive devices. Here is the hardware. This is organic. That could be inorganic, but we done some experiments with organic devices. So how can we use that? Well, first ideas were how that was used. So the first ideas was that the guys used that in neural networks, and one of the idea was that can we create the prosthesis between two neurons? How can we connect two neurons? I mean, biological neurons with this artificial synapse. It's not just let's say artificial intelligence in traditional way. It's more of let's say neuroprosthesis, artificial intelligence in the way that you can integrate artificial intelligence like brain to computer interfaces or some other interfaces. Can you integrate these electronics in the biological neural network? So here you can see to the left, you can see the slice of the rat brain, sorry, the slice of the rat brain with the cell number one, cell number two, well, those are two neurons. They are not connected naturally with natural synapse. And the researchers, they connected that through the schematics, through the electronics that is presented to the right. So they have triggered cell number one. So they put some current in the cell number ones. They have triggered that with the current, and then they started training this membrane device with the response of the cell number one through the schematic, and that response through the membrane device, like a synapse, was conducted to the cell number two. And after the training, they have, you can see that the graphs goes like from blue to red. So at the beginning, there were blue pulses, no response almost. And at the end of there were like spikes, the response of the cell, because the cell started perceiving the resistive device, the electronics, as if it's biological sim. So this is the way we can do this prosthetics, right? So we had the idea that can we create the neuron? So if we have the synapse, why don't we create the neuron? So we created the neuron, and so the neuron we're training in a similar way that you can see in biology. So this is called Hebbian learning. So this is hyperbolic function of the Hebbian learning, and this is the experimental data that we got from immersive devices. It's the same. So the one of the sources of how can we save the energy is that our learning, all the learning processes in biological world, they are solved in the what is called synaptic area. So the synapse itself, it trains by itself. It's not you don't have to use backpropagation mechanism. You can use only one synapse, and by itself, it is like self-trained. It adjusts the weight because of this Hebbian training or Hebbian learning. I'm not going into the details how it works, but you have to believe me that it works with membrane device. So you can actually translate the same mechanism into electronics. So then, hello. Yeah, so we had that idea that can we reuse as simple as we can the circuitry of the spinal cord, because my group we worked with spinal cord trauma. So can we reuse the spinal cord circuitry to re-implement the self-organization, self-learning? So this is really, really, really small neural network. This is only 5 neurons, but we have re-implemented the rehabilitation process of the rat. So the rat is having the complete spinal cord trauma. What it means that it has the complete cut of the spinal cord. And so there is segment of the spinal cord below the trauma. It's not connected to the brain. So from the engineering perspective, we have really small circuitry, biological circuitry with a feedback loop. So you have these 5 neurons. It's called rhythm generator. Then you have motor neuron. Motor neuron is a neuron that is connected to the muscle, and the muscle manages the transfer of the weight of the rat as if it goes through the rehabilitation process from the heel to toe, 1, 2, 3, 4. So you have the activation of the fibers, 1, 2, 3, 4, and the neurons, 1, 2, 3, 4. So this is the schematic. We used static memoristic devices 1 and 2, like LN, static leakage with leakage neurons. And then you have memoristic neurons. That means that you have the learning processes in these memoristic neurons here, or 1 and 2, right? So the input data, let's count a bit later how much that was. So we have to use, so we have this transfer of the weight, 1, 2, 3, 4. The fibers triggered 1, 2, 3, 4. And you see these 200 hertz frequencies that goes sequentially 1, 2, 3, 4 in these fibers, and it's channeled into this. Actually, this is the reservoir, into the reservoir of 4 neurons only. Then you have to have what is called stimulation. You have to trigger the electrical activity because we wanted to reproduce the rehabilitation process. We have to use this 20 hertz that triggers the electrical activity, learning activity of those neurons. And then you have, this is mainly it. So this is mainly the information that you have inbound. And because of the feedback loop, you have this self-learning process. And you can see here is the resistance of memoristic device, of this green memoristic device, that is kind of self-balancing around optimal value. And you can see here that this green output is being placed in what is called right place. And this is the training process that goes for 1 minute only. Then we have done the experiment with 2 memoristic devices or 2 memoristic neurons, this pink and green. And again, you see that after the training, the responses of those neurons were placed in the right place, that were resembling the diagonal pattern that we can see in the rat. So we actually reproduced the rehabilitation process or self-organization process of the rat spinal cord that has been under the trauma. Then we have replaced the memoristic device with the resistor and with a lower resistance, and you can see that the pattern was ruined. So the idea that we can create with this small information, small inbound information, which I don't know, less than 1 kilobyte, the complex pattern that actually it's working pattern, the part of the working pattern of the rat, because of the feedback loop, it has the option of self-organization. So, and later, actually this is electronics, yes. That was done only by electronics. So we have used only the hardware. There is no software, no Python, no C++, nothing like that. We just use electronics as if it is the nervous system. So this is the way that we have used. And then we've done some research. We published the paper that there are actually a lot of feedback loops in the nervous system. So there is the parts, those are the parts of the brain. There is thalamocortical loop, and there are basal ganglia involved in the loop. There is a loop involving motor cortex, spinal cord, sensory cortex, and so on. It's bigger scale with the spinal cord, and so there are a lot of feedback. For example, this is the schematic of the complete schematic of the spinal cord. And what else you can do with that? Okay, I have 2 minutes only. Okay, so for example, we have done the complete model of the spinal cord, which is like that. And okay, again, as I told you, we have been working with the neurorehabilitation process, and we've been thinking of actually neuroprosthesis, but this could be used not just neuroprosthesis, this could be used, for example, at the locomotion drive for the robotics. And you can add navigation on the top of that. And this, again, will consume much less power than digital system, digital artificial neural intelligence. Okay, I'm going to skip that. For example, this is the breaking through, breaking through, let's say, our research done by a group from APFL, Greg Cartin. What they've done, they could even use, similar approach, let's say, similar approach. They're reading data from the motor cortex, and they are processing the data through panel computer. This computer is used, they used hidden Markov model here, and then they've been stimulating the spinal cord, and they could actually make the guy with complete spinal cord trauma with the implantation for sure, because they have to stimulate the spinal cord, walk again in the way, not normally walk, but with this supporting system, he could walk. Right. So our approach, where we got at the end, so this is the schematic of the spinal cord, of the neural network of the spinal cord that we have used, like complete one. But that was digital, not the memory step one. So it consumes a lot of energy. So that's why we could, reused only this device as the external, so we couldn't do the implementation of the device. So you have to have the big computer for that. But if you translate that into a membrane device, possibly you could use only one chip. So, and then we connected that to my leg. So, and it manages, so this is artificial spiking neural network that manages my leg, my limb in the walking pattern. And because we used the injured spinal cord. So you can see that it is the pattern is not that smooth as it could be, but it reproduces the rehabilitation process of the spinal cord. And now you can see that I'm on the what is called body weight support system, and I'm under the stimulation. So the external device, and I can show you the device. This device actually manages my leg, the artificial intelligence, if you like, in general terms, artificial neural networks manages my leg. So this is mainly it. Do you have any questions? I just managed to make it through in 20 minutes. Thank you. Hello? Hello, hello.
Thank you,
Can
sir.
you hear me?
Yes, we can hear you. Any questions? Can I see some questions in the chat so that I'll read for the speaker? There is a question from the students. The question is very generic. They are asking if they have the knowledge of ANNs, because they are studying that as a part of their machine learning course. Can that be effectively transformed to SNNs? That's their question.
Okay. The question is not that simple that it could look like at the very beginning, because the thing is that what I can say, and usually if you go into the neuroscientific sources, you could see this idea of that architecture matters. So in the sense, yes, you can translate ANN into SNN for sure, but there is no guarantee that SNN, like per se, by itself will outperform ANN, because ANN, in ANN, well, let's say traditionally, I should put it like traditional ANNs that reuses Rosenblatt model or convolutional neural networks. They use specific architecture designed for the ANNs rather than SNNs. We have bright example of SNNs, spiking neural networks, as our nervous system. There are some principles already implemented in our nervous system. That's where we got our inspiration. So here, for example, we got this, this is the brain. It has a lot of feedback loops, as I said. So one of the key principles, or spinal cord. It's even easier to demonstrate. So the key principles of this organization of the spinal cord is the feedback loops. So in the sense, you can translate ANN into SL, or you can translate SNN into ANN, but usually it won't work well, or won't work like outperform one on each other, because the principles are different. If SNNs, they exist in the world with time, like a physical dimension, in ANN world, you don't have time. You have only sequence of the input vectors or information, or input information that income that are inbound into the neural network. That's what you have. But in SNN world, you actually have physical time at the physical dimension. You have to take into account time. That's why you are doing that with the differential equations mainly, and you have to solve the differential equations taking into account time. And time plays important role in feedback loops. And the feedback loops plays important role in training or self-training of all these spiking neural networks. So it works together, and you have to take that in account. That it's not straightforward. It's not like you take transformer and put that in spiking neural network, and that works nicely. No, it won't, because the principles are different. But if you implement auditory cortex or language centers, like it is organized in the brain, you could possibly outperform transformer. That's how I put it like that.
Okay. Thank you, sir. There are three more questions. One
Yes,
is there any proof that SNNs already outperformed ANN in terms of energy efficiency or latency?
yeah, sure. Yeah, we have. About latency, I'm not sure what you actually means. SNNs, well, in general, you could make some dirty tricks with SNNs too. You could make it work faster, for example, than biological SNL, right? Biological nervous system. You can play a lot of dirty tricks with that. But this is not like done. This work is not done. We have to understand how we can optimize the work of SNNs. This is not done. You can do it yourself. But yes, we have evidence, and we published the article. Do I have the reference? Oh, I don't have the reference here on the slide. Sorry for this. Okay, I'll find the reference, and I'll send the reference to this article to the conference organizers, or you can send the email to me, and here is my email. Yeah, I can send the article. So we published the article, and this is published results, and we have the evidence that yes, SNNs outperforms ANNs in terms of energy consumption. But you have to take in account what are the approach. For example, ANNs, how we do ANNs usually. So we have, I don't know, PyTorch, we have Keras, for example, on the top of Python. Python is on the top of C++. C++ is on the top of Linux. Linux is on top of firmware, and then on the top of the hardware, right? So we have several layers. How many layers? 5 layers of abstraction, at least, right? So we have at least 5 layers of abstraction to implement artificial neural network. Okay, but how we do spiking neural network? You can do the same. You can use the same stack of technologies. You can implement spiking neural networks on the top of Python. Yes, you can do that. Will they outperform ANNs? No, they don't. They are usually they consume much more energy, because you have to solve differential equations instead of having the Rosenblatt model of the neuron. But if you implement spiking neural network as the hardware, specialized hardware, self-training hardware, yes, you do outperform. You outperform
Okay.
like 6 orders of magnitude. That's what you do.
Okay.
But
So
this is
you meant to say
specialized
that.
hardware.
Okay. So you meant to say that there is large scope in fine-tuning the hardware optimization to make it SNN more latency, energy efficiency, as well as to compete against the latency
Yeah,
in
sure.
complementing ANN. Okay. Thank you so much, sir.
Yes, yes, yes,
There is
sure.
one more one. Can we take up the questions? There are two more questions.
Yes, please do.
Okay. So there is a question by Sagari ma'am. What ethical challenges do we foresee as ANN becomes more widespread?
Wow. That's really good question. I'm not philosopher to answer this question, to be honest. I can just speculate from the engineering perspective.
Mhm,
Uh, well, I don't know. So the thing is that we have, well, we usually look at the SNLs as a perspective to improve artificial intelligence to make it more effective, more robust, for example, implantable things. But
mhm,
hacking, if you have the implantable devices based on the spiking neural networks, if you hack that, you could possibly hack that part of nervous system, and there are a lot of ethical issues connected to that. Will emerge in future because currently
mhm.
we don't have the technology. We're struggling
Okay.
to have the technology first, but then there will be a lot. I can see that. Yes.
Okay. So, are there any promising strategies for overcoming the training challenges with respect to SNNs?
Yeah, sure. So, okay, here is the graph. So, for example, here, what we can see that we have trained, let's say, spiking neural network representing the part of the spinal cord for 1 minute only. In biology, you have to use in rats. So this graph is you can get to this point of the rehabilitation through 40 weeks. So this is the way that we can even now indicate that spiking neural networks, artificial spiking neural networks, let's say, or electronics, implemented electronics, you don't have to copy the things, but you have to follow the rules of organizational spiking neural networks in biological world, and then you can make dirty tricks, what I call dirty tricks. You can make the learning faster
Mhm,
or slower or whatever you like, because this technology is 100% under your control. It's not about the
mhm,
evolution anymore. It's about
mhm.
your technical solution. So you
Technical
can do
solution.
it even better. You can
Mhm,
outperform the nature, but you have to
mhm,
understand, you have to have the solid understanding of the rules and the needs of spiking neural network. And those are feedback loops, those are delays, those are timings, STDP, spike time independent plasticity of the training algorithm, and so on.
Okay, then there is, I think Sagari ma'am is in very much interested with this SNNs. So the last question
Super.
that she's posing is since ANNs are widely used today, yes, we see all applications, and even we are very much close to ANNs than SNN because we are still exploring.
Mhm.
And SNNs are proved with some of the papers that they are more energy efficient. Where do we actually think SNN will make the biggest impact in everyday application apart from medical applications?
I think the autonomous robotics is really promising in this sense. So
Mhm.
I would focus on those two directions: medical plus autonomous robotics.
Okay.
And
Okay.
medical application is really promising too, because you can create the chip of 1 million membranes to device, 1 million synapses, like
Mhm.
in several centimeters, and you can put that in the body, and that will
Mhm.
consume microwatts, not terawatts, but microwatts of
Mhm.
energy, and you could recreate the complete structure of the part of the nervous system, spinal cord or the cortex or something like that, that will help stroke, people with stroke, people with spinal cord trauma, palsy, and those are millions of people around the world. And I'm sure in India, I'm sure all around the world, in US and Europe, everywhere.
Hope we are done. Any more questions? Sagri ma'am, hope we answered your questions.
Yes, ma'am. Thank you, sir.
Thank you, ma'am.
Thank you. So if you have
Okay.
any further questions or you want to do the collaboration, please send me the email. Here is my email. Please feel free. Yeah, thank you very
Sure.
much.
Yes, thank you, sir. Please allow
Thank
me
you.
to have a closing note.
Yes, please.
Yes, on behalf of the organizing committee, the Anand Sagar College of Engineering, thank you, sir. Thank you for enlightening us and giving us an inspiring session that clearly bridged what we need to do and where are we, what angle of research we need to work on. Your insights into ANN and SNN and clearing so many doubts of the participants have given our students and young engineers a fresh perspective on how intelligent, energy efficient system of the future will be designed. We really appreciate your time and valuable contributions, and thank you so much.
Thank you.
Yes.
Have a nice day. Bye.
Bye, sir. Thank you so much.
Yeah.
We
Please feel
also would
free.
like to hear. We also would like to hear more about the ant robotics.
Oh yeah. Okay. Next time, I guess, right?
Sure, sir.
Yeah. Okay.
Yes. Thank you so much.
See
Thanks for the
you. Bye
cooperation.
bye. Thank you.
Bye, sir. Thank you. So, dear participants, we have the next session at 4 o'clock. So you can join at 3:50. Thank you so much.